Rahim. In our lesson, in this video for today, in our lesson for today, we are going to discuss something that is important, and we can expect a lot of questions from this as well. The relationship of intensity with amplitude. We already know what is an amplitude of a wave, but for now, let's first start discussing the intensity of a wave. What does the intensity of the wave mean? Okay, so I'm going to define the word intensity for you, and you should be able to memorize this because you can expect examiner to ask you to define, you can expect him to ask you to define intensity for 2 marks. So the definition is going to be energy passing through per unit area per unit time. Now, this is the definition for intensity. I'll try to explain this to you. Imagine that these red arrows are indicating different waves that are traveling towards the right. Okay, and there is a surface in the path of it. Let's say this surface has an area of A. We can see that all the waves won't be passing through this surface area. Only a few waves will be passing through this surface. The rest of them will be passing above or below it. These red arrows are all indicating waves, and waves are obviously transferring some energy from one place to another. So intensity will be defined as the amount of energy that passes through a surface area in a single unit of time. That means you can simply understand intensity to be the amount of energy that is passing through this surface in 1 second. Energy passing through this surface in 1 second. That's the surface that I'm talking about. So intensity is related to the amount of energy that a wave is transferring from one place to another. We can express this as a mathematical formula. Intensity equals to energy divided by area and then divided with time. Energy over area over time. If I use the symbols for energy, I use capital E. For area, I use a capital A. And for time interval, I use a small t. I can write this to be E over A divided by T. When this division sign turns into multiplication, 1 over A multiplied with E over A multiplied with 1 over T. This T gets multiplied with this A, so the intensity comes out to be energy over area into time. Now, if you remember the energy when it is divided with time, that means energy divided by time, that becomes power. So intensity becomes power per unit area. So here is an alternate definition for intensity. Instead of writing energy passing through per unit area per unit time, you can write intensity is defined as power per unit area. Both of these definitions will be acceptable for us in the examination. And that's the formula for intensity. I'm going to highlight that for you. Energy over area over time, or instead of that, you can also memorize power over area. The SI unit for power was watt, and the SI unit for area is meter square. So intensity is going to have a unit of watt per meter square. Okay, we take a little break here and see if everything is understandable or not. We were trying to discuss the effect of the relationship of intensity with the amplitude of the wave. We know what intensity is, we know what amplitude is. Amplitude is the maximum displacement of a particle from its mean position, and intensity is the amount of energy that's passing through per unit area in a unit time. Now we have to discuss a relationship between intensity and amplitude. Intensity is going to be equal to, directly proportional to, the amplitude square. Intensity will be directly proportional to the amplitude square. You you can ask me why is that or where did that come from? That is not relevant to our syllabus. It is just something that we have observed, that upon increasing the amplitude of the wave, intensity of the wave increases by a factor of 4. I'm going to explain this statement in a little while, but for now, you don't have to actually know where this comes from or who presented this as a law. In our syllabus, they just ask you to recall and use. So you can just memorize this as a fact, that an intensity of a wave will be dependent on the amplitude. Intensity of wave will be dependent on its amplitude, and not just on its amplitude being raised to a power of 2. There are some things that we observed and then we make them as laws. So this is one of those things that is purely based on observation. Intensity is directly proportional to amplitude square. This direct proportionality becomes an equal to, and then a constant k is introduced in it. I is the intensity and A will be the amplitude square. So this forms an equation of the intensity with the amplitude square. All right. This simply means that if amplitude is increased to twice, if initially the amplitude was A and now it has become 2A, so the intensity will be 4 times. That means now if a wave has its amplitude increased to 2A, that wave will now carry 4 times the original amount of energy. If an amplitude is increased to 3 times, the wave will carry 9 times the original intensity. So just to show this fact, 9 times the original energy. Just to show this fact, we have memorized this formula or this relationship as a law, that intensity of a wave will be directly proportional to the amplitude square. Logically as well, if you want to increase the amplitude of a wave, you would have to move the source faster. Thus, it will be consuming more energy, so it will be carrying more energy as well. All right. Imagine this here is a wave, and they tell us that this is the amplitude of the wave. Let's call this to be A1, and let's say that it has an intensity of I1. Both A1 and I1 are given in a question. Intensity is equals to Ka square. From here, K will be equal to intensity over the amplitude square. This K is a numerical constant value. That means it's going to have a constant value and it's not going to change but for a single wave. That means it will change for a different wave, but if I keep talking about this very wave that I'm talking about, the K is going to stay constant. That means even if I make some changes to this wave, Even if I make some changes to this wave, the intensity and the amplitude may change, but the K is going to stay the same for this wave. That means now that I have changed the amplitude of the wave, let's call this to be A2 and let's call the intensity to be I2. So I can simply make the equation that I1 over A1 square was equal to K. So I2 over A2 square is also going to be K. As I am talking about the same wave, only with a different amplitude, it's not a different kind of wave. So the K is going to stay constant for both the cases. That means both these left-hand sides of the equation, I1 over A1 square and I2 over A2 square, both of them, they are equal to the same value of K. That tells me that I can equate the left-hand side of both these equations. We can equate the left-hand sides of both the equations here. Because I1 over A1 square was equal to K and I2 over A2 square was also equal to K. Both these K's were equal, so we equated the left-hand side of the equation with the right-hand side of the equation. That's going to be an important equation for us. This equation helps us to compare the intensities and amplitudes of two same kinds of waves. That means if originally it was a transverse wave, water wave, then afterwards it should also be a transverse water wave. You can't just compare a transverse water waves with a transverse electromagnetic wave. For an electromagnetic wave, K is going to have a different value. All right, I'll show you an example as well. Let's see. And you can actually expect a question like these. A wave of amplitude 10 centimeter has an intensity of 42 watts per meter square. What will be the new intensity if amplitude increases to 20 centimeter? After reading this question, we can understand the sense that it's the same wave whose amplitude is being increased. So just because it's the same wave, which is having its amplitude being increased, this tells us that K is going to be a constant. So this equation is going to be valid for this problem. Let's see, I1 over A1 square equals to I2 over the A2 square. Now just recall the previous intensity and the previous amplitude. The wave has had an amplitude of 10 centimeter. That's the first amplitude. Has an intensity of 42. That's the first intensity. What will be the new intensity? You are asked to find out the new intensity I2. If the amplitude increases to 20 centimeter, that's going to be A2. Now we would just have to substitute the values. Instead of I1, we place 42. Instead of A1, we place 10. Instead of I2, we can't place anything because that's what we need to find. Instead of A2, we are going to substitute 20. That's going to be 42 divided by amplitude is 10. You raise that to a power of 2. It is in centimeter. You can convert it into meter, but it's not going to have any difference. It's not going to cause any difference because amplitude is present on both sides. If I take it in centimeter on one side, I have to take the other side amplitude to be in centimeters as well. Now you need to find out I2 and the new amplitude is 20 and then you raise that to a power of 2. I2 comes out to be 42. Multiply that with 20 square and then divide that with 10 square. That gives me 42 into 20 square is 400 and 10 square is 100, so we can cancel that stuff out. Intensity gives me 168 watt per meter square. That's the unit for intensity. So the new intensity I2 is going to be 168 watt per meter square. This is a sample question. You can expect such questions to come in your exam. Also, something to note here. Intensity increased from 42 to 168 when amplitude increased from 10 centimeter to 20 centimeter. You can see that the amplitude got increased to twice. The intensity got increased to 4 times of its original value. Amplitude, it got increased by 2 times, and the intensity got increased by 4 times. This happens because of the square on the amplitude in the equation. Okay, we take a little break and see if you're following this process. Okay, here is a question. They show you on a graph that this is a displacement in meters against time on second graph, and they also show you the values on the y-axis. 2, 4, 6, 8, -2, -4, -6, -8. They show you that, let's say, this is what a wave looks like on a graph. And they tell you that this is the wave P, and it has an intensity of 24 watts per meter square. Okay, they ask you to draw a graph to show a wave Q with twice the intensity. Frequency or the time period is constant. Now, how to solve such a question here? They're asking you to draw another wave and call that wave to be Q. We have to draw a wave and call that wave to be Q. It has to have twice the intensity. That means if the original wave had an intensity of 24, now Q needs to have an intensity of 48 watts per meter square. We can see from the graph that the wave P has an amplitude of 4. The wave P has an amplitude of 4 meters. If only I'm able to calculate the amplitude of the wave Q, I will be able to sketch that on the graph. If only I'm able to find out the intensity of the wave Q, I'll be able to sketch that on the graph. Now see, we are comparing two waves over here. One is the wave P, the other one is the wave Q. I can recall the formula: intensity of the wave P divided by the amplitude of the wave P raised to a power of 2 should be equal to intensity of the wave Q divided by the amplitude of the wave Q and raise that to a power of 2. The original intensity was 24. The original amplitude was 4 being raised to a power of 2. The new intensity is 48, and you have to find out the new amplitude, AQ. Let's keep that as a variable. Now, if we want to find out the AQ square, it needs to be the subject of the equation. So I take the AQ square onto the other side and take everything else from the left hand side to the right hand side. The 4 was in the denominator on the left hand side. So when I bring it in the numerator on the right hand side, it gets divided with 24 was in the numerator on the left hand side. When I bring it onto the other side, it gets divided. It becomes a part of the denominator. Just to remove this square over here, I would have to take the square root on both sides. So AQ comes out to be 48 into 4 square is 16 divided by 24 and then raised that to a power of a cube root. So this is 4 times 4 is 16, 4 times 6 is 24, 6 times 1 and 6 times 8 is 48. That's going to be 8 times of 4 divided by 1. So 8 times 4 is 32. You take the square root for that. What do you get? What is the square root of 32? The answer comes out to be 5.66. 5.66 meters. So this tells us that the wave AQ, the wave Q that had an intensity of twice its original intensity is now going to have an amplitude equal to 5.66. So we can see that on this graph, this is going to be 5, somewhere in between 4 and 6. 5.6 is going to be even at the center of 5 and 6. So this is where the amplitude of the wave will be present. The new wave. I'm going to join these points and form a very smooth graph. This is what it's going to look like. This is going to be our wave Q. So that's the kind of question you'll be expected to attempt in your past paper. All right, so the next concept that we are going to discuss from this chapter is going to be the Doppler's effect. Doppler's effect. We would have to define it for 2 marks. The Doppler's effect is the apparent change or apparent change in the frequency of a wave if there is if there is relative motion between the source and observer. Now, what does all this means? I'm going to explain this to you by using an example. Imagine I have a little pond of water, a pond, a puddle of water, okay? And here are 2 observers. The red spots, they are 2 different observers, observer A and an observer B. What if in the center there is something that is creating disturbances in the water? Disturbances in the water. That means this little blue dot that I have shown here, let's call it to be the source. That's going to be the source of the wave. If it keeps vibrating in that puddle of water, it's going to continue creating water waves in the water. So we will see the water waves are going to travel in all possible directions. Wherever there is water present, water waves will travel in that direction. All right. How do we represent the water waves? We represent those water waves by using circular wavefronts. Circular wavefronts. This is a circular wavefront. Then this is another circular wavefront. Then this here is another circular wavefront. Okay, you have seen that I have tried to make all these wave fronts at equal distance from each other. This S was the source. This outermost wave is the one that it created when the first time it created some disturbance in the water. As the time passed, that water wave continued to move away, so the wave front started to grow. Then this second wave front, this one, this was created when this source caused another vibration in the water. Then this third wave front was the one that was created when the source caused another vibration. So the first vibration is going to create the outermost wave. It's like a wave is produced and that wave slowly starts to spread out in all directions. So the circle starts to get bigger and bigger, moving away from the center. During that time, when the source vibrates once more, it creates the second wave front. Then when it vibrates once more, the third time, the source is going to create the third wave front. All these wave fronts are moving in all different directions with different speeds. But you can see at every position, the wavelength between these wave fronts is remaining constant. Okay, that means the wavefront 1, wavefront 2, and wavefront 3, they are going to reach the observer B, and they're also going to reach the observer A. As the wavelength is constant, as the wavelength is same on both sides, A and B both observe same frequency. That means the frequency that A will detect and the frequency that B will detect is going to be the same. What does frequency means? It means the number of waves detected per unit time. As the speed of the wave is same, the wavelength is the same. So they are going to both receive the same amount of frequencies at A and at B both. But Doppler's effect is observable when there is relative motion. What does that mean? That means that the source produces a wave, but then the source also starts to move towards one of these observers. Now, this is going to get a little tricky for me to explain. Okay, stay attentive. You might be able to understand it. I'm going to use the same example again. I'm going to redraw the same pond. Okay. All right, that's the same pond or puddle of water that we were talking about. This little circle at the center is the source. When it vibrates once, it creates a circular wavefront. That's the wavefront, with the source being at its center. But as the time passes, this circle will start to get bigger. Why will it get bigger? Because this circle is indicating waves traveling in all directions. And as the waves continue to move away from the source, this circle will continue to get bigger. So this circle I am drawing as a bigger circle now. That means this circle has become bigger as compared to its original size. During this time, this little source here, it moves towards the right. I choose to move it towards the right. Okay. This source is now moving towards observer B and away from the observer A. What if it releases one wave now? What if it releases another wave at this position? Do you see that on the right hand side of both these circles, they have become closer to each other? And on the left hand side, these circles are away because wave was traveling outwards in all directions, but because the source is also starting to move towards the right, so that part of the wave which was moving towards the right, source has now become closer to that part of the wave, hence creating another wave. That is why both the waves become closer to each other in that side of the movement where the source is moving. The source is moving towards right, so the wave fronts are going to become closer at the right side. Now if I wait for some more time, the first circle that was drawn, it will now become bigger, because as the time passes, the wave continues to grow. So FA is going to be the frequency that will be detected at A. FA will decrease because wavelength at A is larger. If we remember that frequency is inversely proportional to wavelength. If somewhere the wavelength increases, the frequency will decrease. So if somewhere the wavelength is smaller, that's where the frequency will increase. Okay, so this tells us that FA will be smaller than FO and FB will be greater than FO. What is FO, by the way? It's going to be the, sorry, I would like to improve the symbology here. Instead of FO, I am calling this to be FS. FS. F instead of FO, because later on we'll be using FO for something else. This is going to be FS, will be the frequency of vibration of the source, which is the actual frequency. That means, let's say the source is causing vibrations at 200 hertz, but the frequency that will be measured for point B towards which the source is moving, it's going to be greater than 200. And the frequency observed at A, it's going to be less than 200 because the source will be moving away from the observer A. Here I'd like to introduce a formula that will be used for calculating these frequencies. FA will be equal to Fs multiplied by V divided by V plus Vs, and Fb will be equal to Fs multiplied by V divided by V plus Vs. Sorry, V minus Vs. V minus Vs. Both these formulas, they are stated in the question paper, so you don't have to know where these came from, but you need to know what are the symbols Fs, Fa, Fb, V and Vs. I'm going to tell you that. Fs is the source frequency. Vs is the speed of the wave, speed of the source, sorry. In the above diagram, we saw that the source started to move towards the right. So it was moving with a speed called Vs. Also, the small v only without any s added subscript is going to be the speed of the wave. Fa is the observed frequency at a point away at a point from which the source is moving away, at a point from which the source moves away. And FB is going to be the frequency observed at a point towards which the source is moving. Now, where do these formulas actually come from? That's not going to be our problem for our course. We don't have to derive them. They are just Doppler's effect formulas. They are, of course, driven from frequency equals to V over lambda, where we substitute a difference in wavelength over here. And we recall that the difference of wavelength takes place because of difference of velocity called the relative velocity. But we don't need to know all of that. We just need to understand these two equations, this one and this one. In our question paper, it's written like this: FO equals to Fs into V divided by V plus minus Vs. We need to know that this FO can be FA or FB. FA is the frequency for when the source is moving away from the observer, and FB is the frequency for when the source is moving towards the observer. Okay, we need to know when do we have to place a positive sign here and when do we have to place a negative sign over here. That is the important part. For that, look at the formulas on top again. To find the frequency for a point from which the source is moving away, you have to add the velocities. You have to add the velocity of the source and the wave. And for a point towards which the source is moving, if you want to find out the frequency for that point, you have to subtract the velocities of the source and the velocity of the wave. Just for perspective, this V for sound is going to be 330 meters per second. If it is a water wave, it's going to have a different speed. Okay, and Vs is the speed of the source that is moving. We conclude our discussion at this note over here for today. This is going to be, we are going to repeat this concept in the next class and try out a few past paper questions from it. Until then, thank you very much.